So the first question dealt with quantum numbers. So we're given a set of quantum numbers. We want to know which one or ones are incorrect set of quantum numbers. And so just to kind of recap on quantum numbers, there are 4 quantum numbers. N refers to the energy level of where an electron is. So these quantum numbers are like an address for an electron. So in a previous session, we talked about the Bohr model of an atom. And we described N as 1, 2, 3. And these were different energy levels inside the atom. And so N describes the energy level. Of course, the higher the energy level, the further you are from the nucleus. And so the energy levels are positive whole numbers. So they go from N equal, not 0, 1, 2, 3. And they can go all the way to infinity. So this has to be a positive whole number. Again, the higher the N value, the further that energy level is from the nucleus. So that's one quantum number that tells us the energy level. The second quantum number tells us the type of orbital. And so usually that's a cursive L, but there's no cursive on this, so I'll just put L, and it's the type of orbital, sometimes referred to as a subshell. You may hear a subshell. And L is dependent on the value of N. So it's restricted on its values based on what energy level it's in. So for example, L can go from 0 all the way to N minus 1. So if the energy level is 1, the only type of orbital you can have is an L equals 0. Now for types of orbitals, we typically use letters to denote the orbital type. So L equals 0, we refer to as an S orbital. L equal 1, a P orbital. L equal 2, D orbital. L equal 3. After F orbital, it keeps on going down the alphabet G, H, etc. These are probably the most common ones that we'll encounter because most elements will have one of these 4 types of orbitals. So L tells you the type of orbital of where an electron is in. So again, you have the energy level. Within energy levels, you have types of orbitals, aka subshells. And then with types of orbitals, you have different orientations of that orbital. That's usually M sub L. And this is called the magnetic. I'll come back to that a little bit. So it tells you the types of orientations of an orbital. And so these are all degenerate orbitals, meaning they all have the same energy. And M sub L is restricted by L. So M sub L can be anywhere from negative L, 0, to positive L. So for example, if L equals 1, M sub L would be negative 1, 0, 1. Now what you have to remember is that each M sub L value holds 2 electrons. Every time you see an M sub L value, that holds 2 electrons in it. So for example, the P orbital, which is L equal 1, would hold a maximum of 6 electrons. And then lastly, we have M sub S, which is the electron spin. And the electron spin can either be plus a half or minus a half. So only one electron can be plus a half and one electron minus a half. So within each m sub L value, you have two electrons, one with a plus a half spin, the other with a minus a half spin. It doesn't matter which one is plus or minus. We'll talk more about that later on. But for quantum numbers, m sub s is either plus a half or minus a half. And that's for every m sub L value, hold two electrons. For those two electrons, one is plus a half, one is minus a half. So just a brief summary of quantum numbers. Now we take a look at the quantum numbers here. We have n equal 4, L equal 3. Can L be 3 when n is 4? The answer is yes, because L is from 0 to n minus 1. M sub L is negative 2. If L is 3, can M sub L be negative 2? And the answer is yes, because if L is 3, M sub L can be negative 3, negative 2, negative 1, 0, 1, 2, and 3. And then can M sub S be minus a half? The answer is yes. So this is a valid set of quantum numbers. Next we have the B. We have the third energy level, n equals 3. And then we say L is negative 2. And so we ask the question, can L be negative 2 when n is 3? And if you look, L can only be a positive number. So therefore, B would not be a valid set of quantum numbers because L is negative and it can't be negative. Next we have C. We have n equal 5. So n is valid. It's a positive number. L equal 1. So if n is 5, can L be 1? The answer is yes, because L goes from negative 5 to positive 5. Can n sub L be 0? The answer is yes, because for the L values, we have 0, 1, 2, 3, and 4. So since L can be 0 for the fifth energy level, we can have an m sub L of 0. And then we have an m sub s of negative a half. That is fine. So C is a valid set of quantum numbers. We go to D. We have n equal 4, L equals 0. So if n is 4, can L be 0? The answer is yes, because again, L will go from 0 to 3. Now, if L is 0, can m sub L be negative 1? And the answer is no, because if L is 0, m sub L can only be 0. So D, or this set of quantum numbers, would be incorrect. Next, we have n equals 7. Can L be 6? The answer is yes. Can n sub L be negative 6? The answer is yes. And can n sub s be plus a half? Yes. So this is a valid set of quantum numbers. Next, we have n equal 2. That's valid. If n is 2, can L be 1? The answer is yes. And if m sub L is negative 1 when L is 1, that's correct. And m sub s can be plus a half. So the correct answers would have been B and D. So here we want to identify the number of electrons in each of the following set of quantum numbers. So for A, we have n equal 4, L equal 2, m sub L equal 2. Now remember, for each m sub L value, there's only 2 electrons that occupy it. Because remember, one is, because of the m sub s values, one is plus a half and minus a half. So for each m sub L value, you have 2 m sub S values. So when m sub L equals 2, it can only hold 2 electrons. Now if we go to the next one, n equal 5, L equal 4. Well, when L is 4, we have this many m sub L values. Since we have this many m sub L values, and remember each m sub L value holds 2 electrons, then this would be a total of 1, 2, 3, 4, 5, 6. We have 9 m sub L values, so this would be a total of 18 electrons. In C, we have an n value, an L value, an m sub L value, and then an m sub S value. So since m sub S value is given, this can only be 1 electron. And then lastly, when you're given the energy level, an interesting or a way to find the maximum number of electrons for an energy level is maximum number of electrons is equal to 2n squared. So if you take the energy level, you square it and multiply it by 2, you get the maximum number of electrons in that energy level. So this would be 98 electrons. As you go to higher energy levels, you have more electrons because you have more orbitals in the higher energy levels. Now we're getting into writing the electron configuration of elements. And again, electron configuration kind of tells you where the different electrons are located inside an element. And so there are three rules that we use when writing electron configuration. The Aufbau principle, which says that you start with the lowest energy level first, fill it with electrons, and move to higher energy levels. And then we have Pauli's exclusion principle, which says no 2 electrons can have the same set of 4 quantum numbers. And lastly, Hund's rule, which says you fill a degenerate orbital first with 1 electron before you pair it up. So all the degenerate orbitals need 1 electron before you start pairing up the other degenerate orbitals. And so shorthand electron configuration is a way we use to describe the electron configuration of elements. So the shorthand electron configuration includes the preceding noble gas and then the important configuration for that particular element. So here we have, for A, we have argon is the preceding noble gas. So argon is right here. Then we have 4s2. So 4s2 is this block here. We have 3d10. So 3d10, if you count from scandium to zinc, that's 3d10. And then we have 4p2. So the 4p2 would be gallium and then germanium. So the element with the electron configuration, argon 4s2, 3d10, 4p2 would be germanium. Next we have krypton 5s1, 4d5. So again, krypton is located here on the periodic table. Next we have 1 electron in the s orbital. So this is the 5s here. And we have 5 in the d. 1, Now, at first glance, you may say, hey, this should be technetium. Well, that's incorrect because 5s1 of 4d5 is one of the exceptions to the filling of the off-ball principle. So for chromium and molybdenum, they get a half-filled S and a half-filled D orbitals. So even though there's 5d electrons, there's only one s electron, so this would indicate that it is molybdenum. So again, molybdenum and chromium are exceptions to the off-ball principle because it's lower in energy to have a half-filled s orbital and a half-filled d orbital. Again, it's only for chromium and molybdenum. So this one for B would be molybdenum. So that's one exception. The other exception is with copper, silver, and gold. Here we have a half-filled s orbital and a completely filled d orbital. So those are the only two exceptions you need to know for electron configuration. You need to make sure that you know the chromium molybdenum exception and the copper, silver, gold exception. So copper, silver, and gold would be, for example, copper would be 4s1, 3d10. So make sure you know these exceptions. Next we have xenon 6s2, 4f14, 5d5. So xenon is located here. Then we have the 6s2. And then you see down here is the 4f14. And then we count 5d5. So the 1, 2, 3, 4, 5. And so here the answer would be rhenium. And then lastly, we have xenon again, 6s2, 4f14, 5d10. So with 5d10, we include the whole block. And we have 6p3, so we count 3 over, and we see it's bismuth. This would be bismuth. Now again, it's very important that you remember the exceptions to the off-ball filling. These are the only two exceptions that we're going to discuss. So with electron configuration, depending on the last orbital filled, we categorize elements as S, P, D, or F block. And so, for example, your group 1 and group 2 elements end in an s orbital, so these are called the s block elements, because all of these elements end in an s orbital, and the row that it's on will tell you the last s orbital that's filled. So since sodium is on row 3, its last orbital will be 3s. Since strontium is on row 5, strontium's last orbital will be 5s. And then for the transition metals, all of these elements end in a d orbital. So this is referred to as the d block. And 1 minus the row tells you what the last d orbital is. So for example, ruthenium is on the 5th row, so that would be the 4d orbital. But all transition metals end in a d orbital. And then down here, these 2 rows of elements end in a f block. And so all of these elements of the last orbital filled would be a f orbital. This is called the f block. And then lastly, on the far right, we have the p block, which means all of these elements end in a p orbital. And so based on where they are, we can designate them as S, P, D, or F. So for example, technetium is a transition metal. It would be a D block orbital. Barium is group 2, so it would be S block. Gallium is down here, so it would be a F block orbital or F block element. Arsenic, located over here, this would be P block. Sg is in the transition metals. It would be a d orbital, and At is also located in the p block. And again, for the p block, the row it's on tells you the last p orbital filled. So that's how we identify elements as S, P, D, or F block elements. So this is the difference between outer electrons and valence electrons. And so for main group elements, outer and valence electrons are the same number. It comes from the highest S and P orbitals. So if it's an S block element, it would just be the highest S orbital. If it's a P block, it would be the highest S and P orbitals. And for transition metals, we'll write transition metals over here. The outer electrons from the highest S orbital. Valence electrons is the sum of the S and D orbitals. So this is how we determine the number of outer electrons and valence electrons, depending on whether it's a main group element, such as group 1, group 2, group 13 through 18, or a transition metal, which is the D block elements. We won't worry about F blocks here. So for arsenic, and also for main group, the group number tells you the number of valence electrons as well. For arsenic here, it's in group 5A or 15. It would have 5 valence electrons and 5 outer electrons. So we wrote the shorthand electron configuration of arsenic. You see that the highest energy level is the 4s and 4p, so that gives you a total of 5 outer valence electrons. Now with zirconium, if we write its electron configuration. Krypton 5s2, 4d2. So for the number of electrons number of outer electrons would be 2. The number of valence would be 4. Now for all transition metals, majority of transition metals are going to have only 2 outer electrons. The valence electrons is the sum of the highest s and d orbitals. Now we go to cesium. Cesium is xenon 6s1. And so xenon only has, since it's a main group, only one outer valence electron. And that's why cesium likes to have a +1 charge. Then lastly, we have iridium. Iridium is electron configuration is xenon 6s2, 4f14, and 5d7. So since iridium is a transition metal, the outer electrons is 2, and the valence electrons is 9. So again, it's the sum of the highest s and d orbitals. Any questions about this one? Okay. So here's kind of like a scavenger hunt. We want to identify the elements, and there could be more than one element that fits this requirement that meets these following criteria. So we want an element with a completely filled 4p orbital and non-valence electrons. So an element with a completely filled 4p orbital would be something that's, if we go here 1, 2, 3, 4, would be something with krypton, xenon, or even radon's shorthand electron configuration in it. Because after krypton, we have up to krypton, xenon, and radon. All of these noble gases have a filled 4p orbital. And then we want to have something with non-valence electrons. So that means it's going to be a transition metal, and if it has non-valence electrons, if we break this apart, it's going to have, in most cases, 2 s electrons and 7 d electrons, because 7 plus 2 gives us 9. So we want to look and see which transition metals, starting with row 5 and below, have 7 d electrons. So we go 1, 2. So 7 d electrons would be something like rhodium, iridium, or Mt. So any one of these elements will have a completely filled 4p orbital and non-valence electrons. And next, so again, rhodium, iridium, or Mt. Any one of those would have been correct. Next, we have an element with a completely filled d orbital and 6 valence electrons. So since it has a completely filled d orbital, it's going to be a main group element. So a completely filled d orbital would be something on row 4 or below. So it would have a completely filled d orbital And it would have 6 valence electrons. So since this would be a main group element, there would be 2s and 4p valence electrons. So something with 4p valence electrons. So we go 1, 2, 3, 4. It would be anything from selenium, tellurium, or polonium. So those would be the 3 elements that could have that condition. So any one of those would have been correct. And then lastly, we have an element with a partially filled d orbital, no f orbitals, and 6 valence electrons. So since it has a partially filled d orbital, it can't be anything up here. It has to start with the d orbitals. And it says no f orbital, so we can narrow down this row and this row. And it has 6 valence electrons. So it's going to be a transition metal somewhere in these 2 rows. And so if it has 6 valence electrons, that means it has 2s and 4p, or excuse me, 4d valence electrons. So we count 2s, 1, 2, 3, 4, 5, 6. You see we land at chromium. So this could be either chromium or molybdenum. They have a partially filled d orbital, no f orbitals, and 6 of valence electrons. So either one would be correct. For chromium and molybdenum. And so moving on to our last question. We want to know which of the following transitions would have the longest wavelength. So very quickly, what we need to remember is that there are 3 types of transitions. The Balmer, I'll start with the Lyman, which is UV, the Balmer, which is visible, and the Paschen, which is IR. And again, the Lyman ends in n equal 1, Balmer ends in n equal 2, and Paschen ends in n equal 3. And remember that as we go from Lyman to Balmer to Paschen, and that should be an n here, we increase wavelength. So this would have the longest wavelength. So what we need to do is we need to first determine which ones come from the Paschen or IR series. And so we're looking for the ones that end in n equal 3. So that would be A ends in n equal 3, and D ends in n equal 3. And the reason we're chosen these 2 is because they're in the IR series, and they're going to have some of the longest wavelengths of the hydrogen transitions. So now we need to look. We have n equal 8 to n equal 3 and n equal 5 to n equal 3. Both of these are in IR, but only one of these has a longer wavelength than the other. And so what you're looking for is the smaller the energy gap, the longer the wavelength. So D would have a longer wavelength than A, because A would still have a longer wavelength than everything else, but since it has a greater energy gap in the IR series, it would have a shorter IR wavelength than n equal 5 to n equal 3. Because remember, energy is inversely related to wavelength. So the smaller energy gap, longer wavelength, larger energy gap, smaller wavelength. So D would be the correct answer.